Recording is rolling. It is Wednesday, October 26th. All right, so we have news about hurricane makeup. Let me switch my screen and show you the email that I'm looking at here. Because there was a Hurricane Ian, of course, we had a few days off. So how I'm interpreting this is that there aren't any additional days we have to show up to school. So I think it's equal number of days. What they're doing is a couple of things. One thing is they're shuffling the definition of when the semester changes. So the first 2 days in January are now part of semester one. I don't know if that means that midterms are still going to be scheduled in December or January. So don't know about that, but I think it's just like a little definition shuffle. The other thing is that there are these 4 Fridays coming up that will be just regular school length. All right, including let's see, is that first one next Friday? Yeah. Right. So not 2 days from now, but the one after that, which is gonna be like regular length school.
Oh, it's just gonna be a full length day.
Yeah, we're gonna have for the
I'm so mad. Are you serious?
yeah. So
I have the
the
sixth period.
way I'm looking at this, it looks like there aren't any additional days that we have to show up to school. So like the day before Thanksgiving, when I don't think that's gonna be altered. All right. So got that. All right, so we got this 3-page energy table. We're gonna do as many things as we can from here, and there's a really special problem with that, like coming up here pretty soon that involves like a car breaking to stop. There's a really classic question involved with that, and along the way, I hope before the end of class, we get to one near the end, yeah, that involves actual universal gravitational potential energy. So I want to tell you guys about that. And I can use this to derive escape speed, right, which I mentioned before, but now I can actually prove to you guys why it is what it is. Okay? And then tomorrow, once I set you guys up with the lab, so if we have time at the end of class day, then I can show you kind of where that's going. It involves mechanical advantage. You can set up work equations and do like that conservation of energy and show mechanical advantage with the pulley system. All right, so that is the plan. Let's get going on this. All right, so it looks like this is how far we got yesterday. Okay. Right. I always get to a little bit different place in my classes, so it looks like we're kind of in the middle of this one, like almost finished this one. Okay, so let's go and do that. Okay. So the kid sliding down the surface. Now, the fact that there is friction, if you just include the kid and sled as an object and the earth as the other object, right, then this friction is acting as an external force, which means it's an open system, right? So it's one of like 2 open systems on this whole packet. Okay, so there's an external force, and the setup's going to be then for an open system, okay, that the sum of energy initial, okay, plus the work done on the system, right? Or it might be minus in this case, right? Because there's like negative work being done, things like that. Okay. So I'll say external, right, is equal to the sum of energy final, right? See, if it was a closed system, I could just say energy initial equals energy final, but for an open system, right, we're going to be adding and subtracting some number of joules to the system, right? Right, so the kid in the slide at the top has what kind of energy? Oh, wait, we went through that yesterday. It's all potential energy, right? So we're going to go mgh at point A, okay? Now the work being done is work by friction, so I can say minus work done by friction. Now, work done by friction, isn't that force times distance, and isn't the distance like full length of the top, right? Okay, so that's why I got it right. And then whatever's left over, see at the bottom he has no more potential energy because he's at the bottom of the hill, right? But he probably has energy motion, right? So I can call that 1/2 mv squared, and that's at point B. And I'm asking the same question for all these scenarios: is what is the speed at point B? I mean, you could ask other questions too. It could be something like that. Right, that's it. Right. Now here's where you can go a number of different ways with this. Do you guys think that friction force is equal to coefficient of friction times the normal force? And you think normal force is mg cosine theta, just like it has been many times over the last few weeks, right? And do you think that if you really wanted to force it, you could like cancel out the m at some point? Yeah, you could do all those things. Now, with this packet, I'm really just trying to keep it big picture. So suppose we just have these variables to work with. You could like solve for VD in terms of these variables. Is that good? Okay. So, actually, you know what? Change my mind. Let's go ahead and do all that extra stuff. Okay. So MGHA. I'll skip a few steps right here, though. I'll say force of friction is coefficient of friction times mg cosine theta. And then L equals 1/2 mv squared. Okay. I don't know if I'll do this with all of my classes, but at least with you guys. Right. Right. So whatever the mass of the kid's sled is, right? Right. So if the kid has a bunch of friends in the sled too, it's not going to change the answer to the question that cop has to go on the bottom. Right. So I need to multiply by 2, take the square root. So VB squared is, see, 2 times all this stuff. So 2GH minus 2 UG cosine theta L. Right. Right. And then okay, so V at the bottom is the square root of all that. 2GHA minus 2U G cosine theta. All right, there you go. All right, sit down. So over here, we're give you guys just a tiny amount of space. I'm gonna say speed at the bottom is, right, it's a big old square root. 2GHA minus 2UG cosine theta times L. All right. Right. It's good. Right. So it looks like, see, the taller the hill is, right, ignoring everything else, keep going faster. Right. But see, it's this trade-off because, right, the longer the greater coefficient of friction or the longer the distance it acts for, right, it's going to slow them down. Right, so we have these like competing effects. Okay. Okay. And I bet if you had an angle that was too small or coefficient of friction that was too large, right, he might like not go anywhere or like come to a stop or something. All right. All right, you guys ready for the next one? All right, so this next one's a really classic physics question, right? A car brakes to a stop. Okay, so open system. I'm just going to look at an open system that consists of only the car, right? That's usually how the question is thrown to you. Right? An open system that consists of only the car. Right? Now, there are other things at play, like the Earth is providing a gravity force, which allows for a normal force, which allows for a friction force. So yeah, sure, that's all there. There's a force from the road, but I'm going to treat that as an external force. That's why I'm calling this an open system. Okay, so I'm really just focused on the car, thinking about motion of the car. Now, if the car brakes to a stop at point A, does it have all kinetic energy and motion? 1/2 mv squared at point A, right? And at point B, well, if it's at a dead stop, how much energy does it have? See, it doesn't have any potential energy because it didn't roll up any hills. It doesn't have any kinetic energy because it's not in motion. I don't see any springs. Isn't it just like 0 energy? Right. Now, hang on a minute. I thought that energy couldn't be created or destroyed. So we had a bunch of energy in joules, and now we have none. Where'd it go? Right. Well, remember, this is an open system. So there's negative work being done by friction force. So it's turning into like thermal energy between the tires and the road. Like if you felt the road before and after, especially put a thermometer on it, the road's going to warm up a little bit, right? Which is not one of our thermal energy. Is not one of our building blocks this semester. It ends up being like m times c times delta t, but that's a thermal thing. Maybe it's spring semester might touch on that. Okay, so here we go. So we got an open system, sum of energy initial minus the work done by friction, you can do like that, is equal to sum of energy final. So we got 1/2 mv initial squared minus force of friction times the distance that the car brakes, which I've labeled x here, so I'll go ahead and put that here. Right, force times distance could be friction force, work done by friction. And we're going to end up with 0 joules of energy, 0 joules. Okay. Is that okay? That's it. Okay. And let's do kind of what we did with the last one with the kid's slide, which say that this force of friction, we can say, well, isn't that coefficient of friction times the normal force? And isn't the normal force just going to be the weight of the car because it's just a level road? Okay. Can I make the substitutions? That okay? Okay. So 1/2 mv initial squared minus, okay, and then in place of this friction force, I'm going to say it's coefficient of friction times the normal force, but the normal force is just equivalent to the weight of the car, right? And then we got the braking distance, right? This is something we've done before, right? Okay. Right. Great. Guys, got that? Right. Let me pause just to make sure, 100% sure that everybody's on board with this. Let's look at a free body diagram of this car. Okay. Actually, you know what? I'm about to make a trip around the classroom. I want to see if you guys get this. Okay. So here's this car. It's moving left to right, right? It's got some initial velocity, right? Of course, it's braking to a stop. Right? Now, while it's braking, okay, car braking to a stop. Okay. Can you guys draw the free body diagram on that car? Okay. Kind of a little pop quiz right here. You draw a free body diagram for that car braking to a stop. All right, so some air. Got it. All right. Very close. Like that. Ah, winner right here. Got a winner right here. Got winner, 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 winner. All right, yeah. You guys get that. Okay. All right, so I've only got around half the room, but yeah. Jump to here real fast. Okay, it looks like you guys are getting this fit. Yeah. You guys got this. All right. Good deal. All right, so you guys said that this car has a weight mg, right? That there's a normal force that is it is equivalent to the weight, so keep that back in your mind because that's helpful. Okay. And then if it's moving to the right but it's braking to a stop, then the friction force is acting opposite of the motion. Okay. And of course, you guys remember friction force is equal to coefficient friction times the normal force, and then normal force is the weight. So friction force, of course, is coefficient friction times the weight. Okay, you guys remember all that? Okay. All right. Okay. And then that friction force, coefficient friction times the weight, that's what subbed in right there for that. Okay. And then times the distance brings you back to work. Okay. All right, so now we're back into this. So if you were to answer the question, what is the final speed of the car, then what's just the answer to this question?
0.
Yeah, 0 meters per second. Okay, so this is 0 joules, this is 0 meters per second. But I've got a different question that I want to answer since we've got this started here, right? And that is, what is the relationship between the starting speed of the car and the braking distance? Okay, so that's the question we're going to continue here. Okay. What is the x as a function of v naught, right? Like if you know how fast you're driving the car and then you brake to a stop, can you figure out how far the car is going to come to a stop? You guys see that? Okay. Right. So let's just solve for this x. Right. So I can take this term, add it over, but I'll put it on the left side just to. Right. So we're gonna have mu mg x. We're solving for x, right? What's the braking distance? That must be equal to 1/2 mv naught squared. Right, that's true. Okay. Oh, guys, what's going to cancel out on both sides? Yeah, mass of the car. Which remember, when a variable cancels, think what that means in physics. That means if you like increase that value, it would make no difference to the answer, right? Right. Right. Hold on a second. Yeah, I want to talk about that a little bit more, but we're like one step away from the answer, which is the braking distance. It looks like it's going to be initial velocity squared divided by. Okay, got a 2 down here. I got a coefficient of friction, and then I got the gravity field of the planet. Okay. So this is the answer to this question, right? Okay. So let's run through different scenarios. So the way this question is phrased, suppose the initial speed of the car doubled. What happens to the braking distance? If you double, say from like 10 to 20 miles an hour, and both cars brake to a stop, say the same tires, same coefficient of friction, same planet, blah, blah, blah. Quadruples. Do you guys see that? What if you have 3 times the speed? What happens to the distance? 9 times. Factor of 3 squared is like 9. Right, you guys see that? Okay. Did we talk about this a long time ago before? Did we? Okay. because we could have, because you could actually just use this equation right here. Right? It feeds into, it's the same idea, right? Initial velocity of the car is something, final speed would be 0 if it brakes just stop. Okay, and then, well, your cars could like sort of slow down at the same rate. That feeds into this. If they have like the same tires, same coefficient of friction. Okay, you guys can I get that? Okay. Okay, so there's a squared relationship. That's the answer to this question. There's a squared relationship, like a parabolic relationship between those two variables. Okay. How about this? What if you triple the mass of the car, but leave all else equal? So we have a little tiny car with a big old truck. Let's say they're driving side by side. They have the same tires, same coefficient of friction between tires of the road. Okay. And then you hit the brakes at the same time. Okay. Which one's gonna go further? The little tiny car or the big old truck?
Wait, triple the mass.
Triple the mass. That's the only difference.
Same.
The same, right? Right? Yeah, because that's what this means, right? Right. So again, that's another one of those classic physics questions. Good chance that it might show up on the AP exam, or and it'll definitely show up in college. If you guys take physics in college, they're going to ask that question. If you triple the mass of the vehicle, all else equal, what happens to braking distance? And the answer is braking distance is the same, because mass doesn't matter. Okay. Okay. How about this? Suppose you increase the coefficient of friction. Okay. So maybe like new tires, or you have a wet road versus a dry road, right? Is that going to decrease the braking distance? Right, so if you have more friction, less stopping distance, right? And then if you switch planets, okay, well, that can have an effect too. Okay. Let's do that. All right. Got next here. All right, so looks like this one we did before, but we hadn't quite finished it out. So let's go to it. Let's finish this problem out that we had started from before. Okay. I really like this setup a lot because it involves lots of these different like building blocks of energy, right? So we got spring energy, we got gravitational potential energy, we got kinetic energy. Right? There's some V up here, some speed. Right, there had it been. It's the only way it got around that loop. Okay. So we'll do now. We're back to closed systems again. So I can just say sum of energy initial equals sum of energy final. Okay. Looks like we got this started the other day. We said the block spring, the Earth would be in the system. Now I'm not including the track in the system because see the fact that it says frictionless. Right. So there is a force from the track, but it's always a normal force. It's only ever a normal force. And the block always moves parallel to the surface, but the normal force, I mean, by definition, normal, that means perpendicular. Okay? So the motion and the force are always perpendicular to each other. Remember in the notes, I told you guys that if you carry a book like horizontally across the room, that carrying force, that lifting force has nothing to do with the horizontal motion. Okay? So you're not doing any work by that force. So that's the reason I'm not including the track in the setup. Now, if I did say there was friction, you'd also have to include the track, and you might want to treat this as an open system. So it's kind of like the last question with the car braking to stop. Okay. But anyway, right, that's that. So we got all the energy comes from the spring, right? We crunch this block against the spring. We got some 1/2 kx squared going on, where x refers to the spring compression, right? And then bam, let it fly, goes around, and then this energy, well, part of the energy goes into lifting the block. That's your mgh at point B. Okay. And whatever's left over is going to go into its kinetic energy and let it have a speed again at point B. Right, right. Is that all right? Right. So yeah, you could solve for VD. You guys think we can do that? Okay, let's do some algebra. Subtract this term over. So 1/2 mbb squared. So we're just doing some algebra practice right here. 1/2 kx squared minus mgh at point B. Okay. Divide both sides by the m, multiply by 2. So VB squared is, okay, so I got a kx squared on m minus 2GHB, because the m canceled, needed 2 up there. And finally, square root kx squared on m minus 2GHB. Right? Is that right? Like that? Okay. And the more of these you saw, these, I mean, you start to see some patterns emerge, right? Like the square root 2GH sure does seem to show up a lot, right? Looks like we're subtracting it because the block is like going uphill, right? Looks like, ooh, the more like the stiffer the spring, if you increase that spring constant, that's going to get it going faster. If that makes sense, right? The more you compress the spring, that's going to get it going faster, right? And, hey, what about the mass of the block? Does the mass cancel out in this one? No, the mass of the block actually matters. Maybe that makes sense too. If you have a little tiny block right there versus you have like a big old block, yeah, the big old block might not even, it might go, and just like run out. It might not even get there, right? If the block's too big, like, right? But a little tiny marble, like go, pew. Okay, so Yeah, so the mass matters on this one. If the mass is too big, then the square root might go negative and don't even get anything. Right, so that's that answer right here. B equals square root kx squared on m minus 2GHB. Okay. Right, so if you're asked us to like solve that on an FRQ or something, but you know what AP likes to do? AP likes proportional type questions. So you could be asked something like, let's see what's a good classic question. Well, this weird. How about yeah, like like if you increase the height of this thing, if you increase the height, what's gonna happen to the speed, right? But then you'd be subtracting off, so the speed would have to decrease. Maybe something like that. All right. Next one. A bungee jumper dives off a platform and barely touches the ground before the cord retracts. So I got a bungee jumper over here. It's gonna fall down, right? And at some point, the bungee cord is going to start to stretch, and then he's going to slow down, and then just like reaches down, like hits, touches the sidewalk, and then like retracts. Okay, so the 2 points is like where you jumped off, let's say like stepped off the ledge, right? And then where he's touching the ground right there, where the bungee cord is like fully stretched. Okay, so for stretching a bungee cord, that sure does sound a lot like a what? Like a spring, right? Ooh, do you think the bungee cord could effectively be treated sort of like a spring, like an ideal spring, right? So we're gonna assume it's like a spring, right? Actually, I said he dives off. Right? You know what? Too, I should tell you guys that this particular problem I did. It is inspired by an actual AP question. Right? They asked it a little bit more complicated, but we're doing like a simplified version of it. So if he dives off, I bet he has some kinetic energy to start with, right? But let's identify the objects in the system. I bet we got the diver, like the person, right? The person jumping off. What else should be in the system? Yeah, the entire Earth, right? Because Earth is providing like a weight force on this person. So if you didn't include the Earth, it would have to be an open system, right? Also, the fact that there's a height change is a red flag that there has to be. You have to include the Earth. Okay? And also the what? Yeah, the bungee cord. The bungee cord. Okay. Because at some point, some of the energy is going to go into that a lot like a spring. Okay? So energy at point A. What type of energy at point A? There's definitely some MGH going on, right? MGH. Right. And if you interpret this word dives as like he like jumps, then you could also say there's what kind of energy? So 1/2 mv squared at point A going on, right? Now at point B, let's see, he doesn't have any height because he's down at ground level, so height is equal to 0. His speed is also just barely reached 0, so he doesn't have any speed, so he doesn't have any kinetic energy down here either. Okay, so where'd all the energy go? Into the bungee cord, and we're going to call that like 1/2 kx squared, okay? Where x is not necessarily this full height. It's just like he's going to fall down some height, and then suppose it gets like about halfway down, and then the bungee cord starts to stretch. Right? It's just this x is just the difference of like where it starts to stretch. Okay, like how much it stretches. Right? Right now we can equate this to this, right? But you guys know the answer to this question anyway, right? Which is what? Well, it would be square root 2GH if he didn't have a bungee cord. If he just like jumped off like, oh wait, I forgot the bungee cord. It's square root 2GH. But if he just like, if he slows down to stop like, and then touches the sidewalk, and then it retracts, okay, then the point that he reaches down, like point touches the sidewalk. How fast is he going? Yeah, 0 meters per second. Okay. But if you want to set up an equation and solve for something else, you could say this plus this is equal to this. Okay. So the energy from here and here all went into here. Okay. Oh, next couple, we got some Atwoods. We got a modified Atwood and the classic double elevator Atwood. Now, if you ask a question like how fast is the block moving after like falling some distance, you have a way to get that already. let's think the old way that you used to do this, which, you could check your answers and she give you the same answer regardless of how you approach this. Right? Which is you say, well, if I know these masses, I know that this guy has a weight, which is providing an external force, which is causing an acceleration. So first thing you have to do is like solve for the acceleration of the system, right? The downward acceleration SWAT. Right? And then you say, well, once I get that acceleration, right, it has something to do with like masses and the gravity field of the planet. Once you get that acceleration, if you know the distance that it moved, you run to this right here and say, okay, I know the distance, I know the acceleration based on the outward setup and the mass of the blocks. If it starts from rest, then I can solve for the speed at the end. Right? So we do have a way to solve this already, right? But we're going to approach this from a new point of view, which is conservation of energy. So I think I need each block, right? And also the Earth. You guys think each block of the Earth? Right? It says no friction, so I don't have to include the tabletop surface. Okay. And energy at point A. Guys, what kind of energy at point A? It's not in motion, so there's definitely no kinetic. There's no springs. So what kind of energy? Yeah, potential energy. Okay. And only involving which block though? Doesn't this M2 have a distance to fall? Right. So I could say like M2 GH. Okay. Now, instead of H, let's do X because I labeled it X. Oops, how about that? But that is a height change, right? Okay. Now this M1, sure, it has a potential energy, but by the time it gets to point B, it has the same potential energy. So I could just like not even include the term, right? If you include it here, you can include it here. It's just going to be a wash anyway, right? Right. So how about at point B? Now, at point B, mass 2 is pretty well getting close to the floor. So we'll call that zero potential energy for mass 2. Right? But hey, are both blocks in motion? So is that like some 1/2 m1 v squared plus 1/2 m2 v squared? Right? Would that be true? Right. Each of those blocks has the kinetic energy, right? In fact, the same speed. I could have said 1/2 of m1 plus m2 v squared. I could have said that. Okay. So let's just set this up and solve for v. Okay. So I got the sum of energy at point A is equal to the sum of energy at point B. The fact that mass 2 is falling is like providing all the energy for the system to move, right? Okay. And so this X is like the height change. Okay. And where's that energy go? Well, by the time we get to point 2, some of it goes to kinetic energy of block 1, and some is kinetic energy of block 2. Okay. Now they do have the same V, so I could like extract this out. Okay. Let me get to that next step. Whoops, M2 GX equal to 1/2 m1 plus m2 v squared. It can do like that, right? Okay. And then we're just a few algebra steps away from solving for the speed. So cross multiply 2, divide this supermass. Okay. I'm gonna get v squared. This at point B, of course. Okay. Is equal to, I got 2 m2 gx all divided by the sum of the masses. Right. Is that all right? Okay. And then last step is the square root. So the speed at point B is a big old square root 2 m2 gx over m1 and m2. Big square root. Okay. So I'm gonna write that in here. So speed at point B is big old square root 2 m2 gx on m1 plus m2. Okay. Let's go. All right. Okay. And then a good thing to do, let me extend this square root a little bit. So definitely square rooting everything. Good thing to do in physics is to play around with this, right? Navigate this bit. Okay. So like, right. Well, it looks like the further distance. Oh, before you, right? Remember, if you did this the other way, if you did like solve for acceleration and then go through kinematic motion, blah 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 blah, right? You would get the same answer. Right? And if you want to check that, you could, but it would be the same answer. Okay? You can plug in some numbers, play around with numbers, and get the same number answers. Okay. Right. Let's look at variables relationships. Okay. So if you increase this height, suppose you like do 4 times the height drop. Suppose you have like a tabletop that's like 4 times the height. Okay. Guys, if you quadruple that height, what's going to happen to the speed? What is the square root of 4? double, yeah, right? Because square root of a factor of 4 would be 2. Okay. How about what if what if M1 was equal to 0? If M1 is equal to 0, then shouldn't it be the same as M2 is just a perfect free fall? You just drop M2 and goes perfect free fall. Okay. Let's see what if that is consistent with something that you guys already know. Right. So let's set M1 equal to 0. If M1 is equal to 0, so it's just like an empty string, isn't it just this? Right. Oh, but then what is M2 over M2? That just cancels. And so would it just be square root 2gx? Hey, that's like square root 2gh. Right now we're just back to like the Galileo problem, right? Which of course has to be the answer. Right? You guys see that? Right? What if M1 is very large compared to M2? Like M2 is like a paper clip and M1 is like a kilogram. Okay. Again, there's no friction up here. Okay. Well, if that's true, then let's see if M2 is very small compared to M1, then this ratio right here approaches 0. It won't be exactly 0, but it approaches 0, which say that BB is getting like very small. But that makes sense too, doesn't it? Okay. Let's go to the classic outlet, the double elevator outlet. Okay. Again, you could solve for acceleration first. Okay. Let me remind you guys how to do this, even though this isn't like conservation of energy, right? Notice with conservation of energy, I've never said anything about how much time elapses on any of these, right? Nor have I said really anything about directions. So because these are all scalar values. Right? Let's go and solve this both ways. We'll solve it both ways. The old way of doing it is to say that the acceleration system is, remember, it's this weight minus this weight, the difference in weights divided by the sum of the masses, which just simplifies to difference of masses over sum of masses times the free fall rate of the planet, right? Right. This is the old way of solving this. Okay. And once you get the acceleration, then you can kick over to v final squared equals v initial squared plus 2ax. But instead of 2ax, I'll do 2g8. No, sorry. Let's do 8. Right. It's not g. Oops. It's this. So a. Right. But h, I live a the height change h. Okay, so it's still h. Okay. So it starts from rest, so this number just goes to 0 meters per second. And then this whole expression feeds in right there. Right? Wouldn't that be true? Okay. So then, and the last step would be to take the square root. So if you want to get the speed, the final speed, I just need the square root of all that. So it's a giant square root. And it's this right here. So 2 times, and then instead of a, I'm going to write this whole expression. Difference of masses over sum of masses times gravity field. Okay. And then also times the height change. Phew. Okay. So that's the old way of approaching this problem. Okay. I mean, it's the correct answer. It's just a different path through the forest, right? Okay. But our new way of doing it, which again should lead to the same answer, I just want you guys to see that it does, is we're going to do conservation of energy. Right. So let's hold on to this and just I'll bring this back on screen, but let's put this aside for a moment. Okay. And say I have M1, M2 in the Earth in the system, just like the last one. Okay, so closed system. Okay. Energy at point A. Well, I do see that M2 is elevated. So do you think that M2 has some potential energy? MGH, right? And then by the time you get to point B, well, I'm thinking the energy went into 3 different places. One thing it had to do was lift M1. So I bet M1 has some potential energy by the time it gets to the final state. Right? You guys see that? Okay. Plus, each block is in motion. So I got some 1/2 mv squared. For each block, right? Is that true? So the fact that the large block was falling was supplying the energy. And like the demand for this energy, well, it divvied into 3 parts, right? Lifting the smaller block and also giving each of the blocks a speed. Okay. So let's set up conservation of energy right here. Sum of energy initial equals sum of energy final. Okay. So we got M2GH turns into M1GH plus 1/2 M1V squared plus 1/2 M2V squared, where V is like the final speed, right? And And see, that's what we're solving for, right? Solving for that. Right. So energy, right? Okay. Now, I know we're solving a bunch of these in terms of variables, which is what I want you guys to do, but a little bit different perspective. Suppose this was like 12 joules, and this was like 4 joules. You'd have 8 joules left over, right? 12 joules. Okay. Just thinking, I'm gonna scratch this out. This is it. Okay, so like 12 joules could turn into like 4 joules plus, and then this might be like 3 joules and 5 joules, for example. I'm just making up numbers, but see how it would like equate the number of joules. Okay. See, if you had a mass and a height change and well, you could plug in number. You could always plug in numbers. Okay. But now, since you guys are AP, first let's solve in terms of variables. Can you guys see that solve in terms of variables? So I'm going to subtract this over. I'll extract I'll pull this out at the same time. So I got 1/2 m1 plus m2 d squared, and that's equal to the difference of these potential energies. So, and I could pull out the GH while I'm at it. Okay, so I cut through a few algebra steps there, just saves a little bit of time, but you could do a little algebra shuffle and get to that. Then you can take this, divide it down, cross multiply the 2. So b squared is I'll have a 2 m2 minus m1 GH over m1 plus m2. And then last step is take the square root. Okay, so now you can have any sets of masses, any height change. You could even switch planets if you wanted to. And you have like this master expression that could answer this for like any Atwood. Let's see, how does that compare with the old method of doing it, where you solve for acceleration first and then jump back to kinematics? It's the same thing. You guys see it's the same thing? Right, either way. Okay. So old way of doing it, new way of doing it. Now you guys got more options. Okay. Right, that's it. All right, so I'll copy this here real fast. Square root 2 m2 minus m1 GH over m1 plus m2. Okay, just like that. Okay. Guys good? So these equals. Okay. All right. I like a lot of these questions coming up here. Right, might have to save this for next week because I want to get to this one today. Okay, so let's jump down to this very last one. 2 asteroids start from rest and gravitate closer to each other. Okay, so what's in the closest dome is each asteroid. Okay. Okay, so they each have mass m, so this is m and this is m, right? Now, what's the energy here? Now, if they start at rest, there's no kinetic energy. I don't see any springs, so it is potential energy. But here's the thing: as they get toward closer to each other, the gravitational strength also increases like significantly. So it is potential energy, but we have to use the universal form of potential energy, which is this one right here. Okay, negative GMM on R. So it's negative G times the mass of this guy times the mass of this guy. I made them say masses, so you could say m squared if you want to, divided by the distance between them that starts, which is R sub A. Okay. And the energy at point B is going to be, well, we're going to have less potential energy, so negative G M on RB. Okay. Now, do you guys see the fact that they're closer together? If you're dividing by a small, guys, if you divide by a smaller radial value, does that blow up your fraction bigger? But also it's negative. So if you have a bigger negative number, isn't that like less than, right? Like -7 is less than -3, right? Because some of that energy went into kinetic. 1/2 mv squared for one asteroid plus another 1/2 mv squared for the other asteroid, right? Okay. So like falling towards each other. Is that right? You can like solve for that v. So we got sum of energy initial equals sum of energy final. Okay. We're going to have negative G M on R is equal to, let's see, so that's RA equal to negative G m on RB plus 1/2 mv squared plus 1/2 mv squared. Okay. And since the asteroid is the same mass, you can like, factor some stuff out here. So I'm gonna add this over, clean this up. 1/2, well, 1/2 times 2 mv squared is equal to GMM on RB minus GMM on RA, like that. Okay, and then looks like this mass is going to cancel. Yeah, and do that right. Yeah, one of these m's cancels. Okay. And then the speed would be well, the square root right here. So square root GM on RB minus GM on RA. Okay. If you wanted to combine the fraction and get a common denominator, you could do that too. Just be a different way of writing it. That's all right. Okay. But I've been wanting to show you guys how to get escape speed. You have to use this universal form of escape speed. There's a potential energy to get that. I also want to show you guys that this does simplify to MGH. Okay, go ahead. Oh, yeah. Speed at point B. Yeah. It's a speed at point B. Yeah, yeah. All right. So do you guys remember how force is equal to GMM over R squared? Right? So two masses gravitationally attract just between them, right? And I know if I have force times the distance, that could be like work, which also represents the potential energy that you give something, right? Like if you're lifting something against gravity. Hey, what if the distance that you move it like sort of like is the R, right? So if I do like force times R, right, then I can get like universal potential energy. So I'll call it U for potential energy, right? Gravitation. Okay. And I'll tell you guys why it's also negative. Okay, negative. Okay. So here goes the story. Suppose you have two objects that are in like a big old universe. Right? I have a planet on one side of the universe, and on the other side of the universe, I have this guy right here. Okay, and they're separated by a huge distance, but otherwise it's an empty type universe. Right? There's nothing else. It's just a huge distance that starts out. Okay, now these two are going to pull on each other gravitationally, and they're going to start to gravitationally attract. Okay? Maybe the planet's like a really big mass, like capital M, and maybe this little mass, like 1 kilogram, so like little m. Okay, so over the course of like a billion years, they fall toward each other, and right, and they'll eventually crash into each other. Now the planet's not going to move very much. This one's going to move like pretty much across the whole like universe, and like bam, and then they'll like crash like a billion years later. You guys get that? Right, right. And I wonder what that crashing speed would be. What would that crashing speed be? Right. So let's figure that out. So I could do conservation of energy. Sum of energy initial equals sum of energy final. Okay, where the initial energy, I'm going to start it out by saying it's zero mechanical energy. Like everything is just floating around. There's no kinetic energy. But I'm also going to treat this as saying like there's no potential energy either. Okay. And then in the universal sense, potential energy is only ever negative. Right? This makes sense, but it'll work out. So to start with 0 joules of energy in the system ever. Okay. And then as they fall toward each other, they're gaining kinetic energy, but kinetic energy has to come from somewhere. Can't create energy. So the potential energy just becomes like more and more negative, right? That's how you lose potential energy. You just go from 0 to negative. Okay. So I'll do negative GMM on R, okay, plus 1/2 mv squared. Is that okay? Okay. Now, at some point when they crash into each other, bam, won't this R just turn into this capital R, radius of the planet? Right. That's when they smash into each other. It smashes into that planet surface to be capital R. Is that okay? Okay. So I want to see what happens right then. So I'm going to change this generic R to specifically capital R when it smashes into the planet. Okay. And I want to figure out what is the speed. Right. Well, I have to add this term over. So now we got 1/2 times the mass that's falling times speed squared equals. Here, I'm going to change this to mass of planet. There we go. Mass planet. Okay. Positive GMM over R because I added it over. The mass of the object falling from the edge of space cancels. right? The mass of the planet is very large compared to it, right? Times 2 square root, and the crash speed, again, falling from the edge of the universe it's not infinite, right? It's finite. It's the square root of 2gm on r. Okay. All right, so if you dropped an object from the edge of space and it crashes into a planet, it's going to crash with the speed, right? You describe constant mass of the planet, radial size of the planet, okay? That expression will always answer that question. Okay, so if I turn around and ask a different question, if I were to throw this straight up into the air, how fast would this have to go so that it can just barely escape gravity and go all the way to the edge of space? Like, what's the minimum speed? Well, this is the same answer, just turned around the opposite direction, isn't it? Right? Therefore, this also represents escape speed. It's the same thing. Square root 2gm on r. Okay, right, is that right? Okay. No, escape speed is how fast you have to get going so that you can cut off the engines and your rocket could just like coast, and maybe it's slowing down along the way because gravity's still tugging on it. They have enough speed to get away, right? It's not going to be in orbit anymore. Okay. You guys remember orbital speed ended up being square root gm on r, which you guys should be able to derive also. Okay. And now we've got escape speed is square root 2gm on r. Okay. So in general, escape speed is equal to the square root of 2 times your orbital speed. Okay. You guys got that? You guys right so far? All right. Tomorrow, I'm gonna set you guys up in the library. I'm gonna have you guys build some pulley systems. So let me flip my screen just to show you guys an example of this. Here we go. All right. Do you guys see some pulleys, some string, right? Some live weights, the whole deal, right? Now, think about how this is going to work. You know what? Got a better version of this. All right, I'll show you guys this animation at the top of the class tomorrow. But we got these 2 kids trying to deal with the like lifting a pulley, right? And by near the end of this animation, they come up with this rig system, right? So do you guys see like this pail could have some weight, right? This pail could have some weight. But look at the pulley system they've rigged up. You guys see this bottom pulley is like a movable pulley to like move up and down, right? And the way the strings are like wrapped around. You guys see that? Suppose the weight of the pulley was like, or the weight of the pail was like 100 newtons. You see, it's going to be split 3 ways. Do you think the tension of the strings is going to be closer to like 33 newtons? So she only has to pull with like 33 newtons of force to lift 100 Newton. Okay. Good. So you get a mechanical advantage, like a 3-to-1 mechanical advantage. You essentially amplify your strength like 3 times as strong, right? All right. So we're going to add a little bit to that. That's going to be the basic premise of what I'm going to have you guys do tomorrow. So you'll be back in the lab area with some string, working with your hands. Right. All right. So I will see you guys then. All right. See you guys tomorrow for pulleys.